Hello everyone, welcome to this new video. So in this today's video, we'll be solving the problem AVL tree insertion. So this is a hard level problem and it's the problem of the day on Geeks for Geeks today. So the company tags of the question are Morgan Stanley, Amazon, Snapdeal, MakeMyTrip, Oracle, and few other three companies. And topic tags are binary search tree and tree data structures. Great. So now let us go to the question. So given an AVL tree, what do you mean by AVL tree? AVL tree in the sense binary search tree. So before you proceed further, it's expected that you understand the definition or you get familiarized with what is a binary search tree, what you understand from it, what are the conditions of a binary search tree, and then proceed further in solving this question. All right. So given an AVL tree and n values to be inserted in the tree, write a function to insert elements into the given AVL tree. So this is pretty straightforward. It's like they're asking us to construct the AVL tree. Great. So there'll be some set of values that are being given to us and we need to keep inserting them. So note that the tree will be checked after each insertion, and if it violates the properties of balanced BST, an error message will be printed followed by the in-order traversal of the tree at that moment. All right. And if instead all the insertions are successful, in-order traversal of the tree will be printed. Insertions are successful in the sense all the conditions of the BST are met after you are actually trying to insert the values. Let us assume out of the 10 values you have you're on the 4th value right now and you have inserted it correctly. Then all the insertions are successful at that point of time and in-order traversal will be printed. And if your 4th insertion is wrong, it's at the wrong place, then it will be showing an error message. All right, that's what it's telling. And these are the examples. We'll go through that in brief. And okay, so expected time complexity is O of logN and auxiliary space is O of height of tree. To be honest, these really do not make any sense here, because this will not really help you in framing your approach or something. Like this is a classical approach that you need to follow to insert the nodes one by one into your AVL tree. All right. And logN, in the sense, I hope you have went through the BST, you'll be finding that the height, okay, the height of the AVL is logN. All right. So that is one of the reason. And auxiliary space is because that is a recursion stack space that you are going to use, and that will also go up to O of height of tree. Great. And n goes up to 2000 starting from 1. So this is the whole introduction about the question. Now let us go through the example that has been given. So this is the example that has been given to us. So these are values, and after the final the final AVL tree, AVL tree looks like this. Final AVL tree looks like this. So how are we going to proceed further? Now let us first just understand this example. Let us construct this example. Starting, we have 21. Okay, so let us just write that 21. And now okay, before that, let me clarify that. Okay, or else we'll just proceed with this example, then we'll talk about this. 21. Okay, and now we have 26. Okay, I'll just erase this. 21 is done. Now we have 26. So where do you insert 26? Because 26 is greater than 21, you insert that to your right. Okay, 26 is inserted here. And now come to 30. So where do you insert 30? 30 is like greater than 21, so come to your right side, and 30 is also greater than 26, so come to its right, come to the right side. So 30. Now if you carefully observe, is it a BST? Till the second point, it is a BST. The reason being, only the tree was like this, only this much is there, and it's fine. But now it's not a BST. The reason being here, if you see, the right subtree height is 2 of 21. Right now, if you're standing on this particular point, what is the right tree height? That is 2, right? That is 2, because there are 2 levels of depth. And what is the left? 0. There is nothing to its left. 21 is left. And now what is the difference between these two? 0 minus 2, that is equal to minus 2. And this doesn't come in the set of minus 1, 0, 1. All right. So if your difference of left subtree and right subtree, the heights of left subtree and right subtree is in this particular number, like is in this particular set, either it's minus 1 or 0 or 1, then it is a balanced tree. But right now it is minus 2, which is not belonging to this set, so it is not balanced. So how do you make it balanced? So if I just erase these particular things, so I can make it balanced by putting 26 as the root. Okay, 26, and to my left I can have 21, and to my right I have 30. Great. I hope you people understood. How are we constructing this? How are we going to code this? We'll see all these things later. Right now we are only understanding the example. How is this final output is the required answer? That is what we are understanding. All right. Now let me erase this particular thing. So we are done with the third iteration as well. So you also make sure, is it following the rules of BST? Yes. 26 left is 21, which is less than 26. 26 right is 30, which is greater than 26. Everything is fine. And also it is balanced, because the height here is 1, the height here is 1. 1 minus 1 is equal to 0. It belongs to the set. Okay, so this is fine. Now come to the fourth entry. This is 9. So when you do it, so 9 goes to the left of 26. Okay, and again 9 goes to the left of 21. So this is how it is, and it is balanced. Yes, it is. There is no violation. Like here the height is 2, here the height is 1. So 2 minus 1 is equal to 1. It's still in the set, right? So yeah, it's fine. And now come to the fifth value that you're going to insert, 4. Now when you're going to insert 4 is less than 26, go to your left. 4 is less than 21, go to your left. 4 is less than 9, go to the left. So this is how it comes. And now, is this a BST now? No, it is not a BST, because it's not balanced anymore. You see that here the height is 2 for 21, but to the right it's only 0, right? So here 2 minus 0 is equal to 2, which doesn't belong to the set. So this properties of having the left values to be less than root value and the right values to be greater than root value, and the difference between the left subtree and right subtree must be -1 or 0 or 1. All these rules must be satisfied by each and every node. It's not just that you'll be satisfying only to this. No, that's not the case. You must be satisfying for this, every node. All right. Now we see that it's not being satisfied for this. So how are we going to change this? So what if we have like this 26, 20, or or what we can do is we can just put 21 here, okay, 21 here, and to the right I'll be putting 26 and then 30, and to my left I'll be having 9 and I'll be having 4. Okay, so that is this valid tree now? Yes. 21's right is 26, fine. 26 right is 30, fine. 21 right left is 9, fine. 9 left is 4. Everything is balanced now, right? There is no objection as of now. So we can even remove this. So we have made the tree balanced till this particular point. Okay, now come to this other part. So last one, 14. Now 14, where you can insert 14? 14 is less than 21. So come to your left. So 14 is greater than 9. Come to its right. So add 14 here. Fine. Now it's still balanced? Yes. Is it balanced for 9? Yes. Is it balanced for 21? Yes. Because here the height is 2. Here the height is 2. So 2 minus 2, 0. That's completely balanced. Great. So we'll even erase this part. And lastly, so I'll write it properly so that you people will not be having any confusion. So this is 26 and this is 30. Great. And now what is the last thing that we need to insert? 28. So where are we going to insert 28? 28, if you carefully observe, that is greater than 21. So come to its side. That is greater than 26. Come to its side. Now that is less than 30. So you might be inserting 28 here. But now it's not following BST anymore, because for 26, you see that the left side height is 0, but the right side is 2. So 2 minus 0 is equal to 2, which does not belong to the set. So it will be removed. So how can we do this? What is the other approach? We can put like this. So we can just erase this part. Okay. So we can do this fashion. 28 here, 26 here, and 30 here. Great. So in this way, everything is balanced. So these are balanced anyways. Come to the 9. So 9's left is 4, less than 4. 9's right is 14, greater than 4. 9 greater than 9. Great. 9's left is 4, which is less than. 9's greater than 14 to the right of 9, which is 9 is less. So all these properties are matched, and also the left, is it balanced? Like the height of left tree and right of right tree, the difference is 0. It's fine. Same is the case here. So it's like this and like this. Fine. And same is the case with 21. So 9 and 28 is satisfied. Same is the case with 21. 21's left side is 9, which is actually less than 21, so it is also satisfying, and 28 to the right of 21, and which is greater than. And also the height, here it is 2, here it is 2, so 2 minus 2, that is equal to 0. Everything is being satisfied. So yes, I'll just erase these points now. I hope you people are understanding why is this a required answer. All right, we are just understanding how is this a required answer. We are not still framing the approach. We are just understanding how is this the final answer. Great. So I'll just erase these points. So that is the reason, if you can just see if our final AVL matches with the thing that we have constructed now. Great. So I hope you people understood. Now I'll just erase these points. Okay. Fine. I'll just take this off. Okay. Fine. So I'll even erase this. Take this off. The sample examples, and yeah. So done. Now let us list out the properties of a BST. So how are you going to verify, or how are you going to check, or what are the properties that you'll be keeping in your mind while constructing the BST? So the properties are: first property is left side values should be less than, strictly less than, node value, and that should be strictly less than right side value. Okay, right side value. When I say strictly, that means your tree is not going to have any duplicates. It will be constructed by only unique values. All of them will be distinct. Okay, so no value will be repeated once again in the tree. Everything to your left of your particular node, let us assume you're standing on this particular node, all the values to the left of this must be less. All the values to the right side of this must be greater than. Okay, must be greater than your node. So this is one of the property that you need to keep in your mind. Now second one, what is the second one? Height in the sense maximum height. Okay, height of left minus height of right. Okay, this is the balance factor. This is basically nothing but the balance factor, and this must be -1 or 0 or 1. Okay, so height of left minus height of right must be either -1 or 0 or 1. These are the things that you need to keep in mind. These are the two properties. That's it. You'll be revolving only around these two properties. Your question will be solved only based upon these two properties. If any of them are being violated, then you do the necessary action. Then you take the necessary action. So how are you going to do this? Now let us assume I've given this task to you. Okay, now I've given this task to you, and what is the first thing? What is the first thing that you'll do? You'll go to this rule, right? You'll go to satisfy. You'll try to satisfy this first rule. What is the first rule? Now you have a binary tree like this, binary search tree. All right, you have a binary search tree. Initially you have something like this. All right, and now you're trying to insert. I'll just erase this. Now you're trying to insert some value. Okay, now you're trying to insert some value. I've given you value, and you're trying to insert. And now you have inserted here according to the rule, according to the first rule. The node sets here. The node according to the only first rule. Don't forget about second rule now. Okay, do not worry about the second rule. Only according to the first rule, the node can be settled here. The node can be put here. Okay, now see the second rule. Okay, now see the second rule. But when you see the second rule, you see that that the height here is 2 and height here is 0. So 2 minus 0 is equal to 2, which is not correct. It must be only minus 1 or 0 or 1. Now you will try to satisfy the second rule. Okay, first what you are going to do is, according to the first rule, you will insert some at the correct place. Correct place in the sense, according to the first rule, you will be putting it at the correct place, not according to the second rule. Leave about the second rule when you're considering the first rule. Okay, so put it at that place where your left side values are less than node value and less than right side values. You must satisfy this condition. First do it. Okay, once you do it, now you check for the balance factor, and if your balance factor comes out to be less than minus 1 or greater than 1, in these two cases, yes, that means your balance factor is wrong. It must be corrected, and for that reason you need to do some necessary modifications. So what are those modifications? That we'll see right now. Okay, so I'll just erase this point. I hope you people understood what are the modifications and when we need to do the modification. We did not understand, like we did not go through what are the modifications that we need to do. We just understood like when we need to do the modification, when your balance factor is less than minus 1 or greater than 1. In that cases you need to do the modification. The first thing is you insert the value according to the first rule, and then you do the modification if required. Okay, if required. So now you're going to ask, now your second doubt is, what are the modifications at like how are we going to identify what are the exact modifications? If you do take lot of examples and do all those things, like do the manual testing, like taking several type of examples and doing, there are broadly 4 type of examples. Okay, there are broadly 4 type of examples. I have listed them out with the help of example. Okay, so there are 4 categories of modification that you need to do. 4 categories of modification. So 4 categories of modifications. So what are those modifications and all? We'll see that right now. Okay, there are 4 categories of modification that you broadly need to do. So we'll see that right now. Okay, so this is the first case. That is, this is the first modification. We'll identify what the modification is, and we'll identify what are the changes that we are doing, and we'll name it also at the end of this first case dry run. Okay, so let us assume this is the initial binary tree that has been given, and now you're trying binary search tree. Okay, BST. So in this BST, now you need to add the element 4. Okay, the node 4. So let us assume I'm adding it. So I'll just copy this particular tree. Okay, I'll just copy this particular tree and I'll okay, so putting this tree here, we have 9, and now once we have added 4, where are you going to add 4? Follow the first rule. What is the first rule? Add the 4 according to the first rule. So you'll be going to the left of 14. You see that 11. 4 is still less than 11, so go to the left. 4 is still less than 6, go to the left. 4 is still less than 5, go to the left. So now you insert 4 here. Okay, according to the first rule, 4 settles here. 4 sets here, very perfectly fine. Alright, according to the first rule. Now see the second rule. Now calculate the balance factor. What is the balance factor of each of these things? So the balance factor for 4 is 0. For balance factor of 9 is 0. Balance factor of 17 is 0. What's the balance factor of 5? That is left subtree height minus right subtree height. That is 1. What's the balance factor of 6? Left subtree height minus right subtree height. That is 2 minus 1. That is actually equal to 1. What is for 12? 0. And what is the balance factor for 16? Minus 1. Okay. What is for 11? That is 3 minus 1. That is actually equal to 2. And for 14, what is it? 4 minus 2. That is actually equal to 2. Now here the problem is being created, isn't it? Here the problem is being created. From here we do not want to, because here it is 2 and that it's being gradually, the problem is being continued to the nodes above it as well. So the main problem is here. Now we need to rectify this. Great. I'll just erase these points. Now we need to rectify this. How are we going to rectify? Observe this carefully. Because we have added 4, the problem has been created, isn't it? Because we have added 4, the problem has been created. Now if you carefully observe, 11 is indeed greater than 6, right? 11 is indeed greater than 6. What if we have 11 to the right side of 6 itself? Instead of being created here, instead of being having 11 here, what if we have 11 to the right side of 6? Then in that case, we can actually reduce 11's balance factor, isn't it? 11's balance factor can be easily reduced if we actually put that to the 6, isn't it? In that case, when we put that 11 to the 6, when we put that 11 to the right side of 6, you will not be having all these points to the left side of 11. I hope you are getting it. You will not be having all these particular things to the left side of 11, like to the bottom of the 11. So your balance factor will be reduced for 11, isn't it? It will be reduced. So in that case, we can actually find a better better arrangement which actually satisfies the second rule. So what am I trying to tell is, let us rotate this 6. Okay, let us rotate this 6 towards the right. When I'm trying to rotate the 6 towards the right, what am I meaning? What am I going to do is, so the second transition is the final transition. So we'll be having 14 here, we'll be having 16 here, we'll be having 17 here, and to the left I'll be having 6 instead of 11, and to the right of 6 I'll be having 11, and to the right of 11, that is originally that is there, well, that would be there, and to the left of 11 I'll be having 9, and to the left of 6 I'll be having 5, and to the left of 5 I'll be having 4. I hope you people understood. So when I do the right rotation, when I do the right side, this is right side, right? This is right side rotation. This is what I'm doing to the right side. From 6 I'm doing the right side rotation. When I'm doing the right side rotation, the 11, let us assume this is where I'll just write this as A. Okay, I'll mention this as A, and this is B, this is C. Okay, A, B, C. So please don't confuse, like this is B, this is C. Okay, A, B, C. So when I'm doing the right side rotation, my A is being like if I just write this, B is basically A's left, isn't it? A's left. B is basically A's left, and C is B's right. C is B's right, isn't it? C is B's right. And now when I'm doing the rotation, my B's, okay, B's right, I'm substituting it with A. Okay, B is right. What is A? A is equal to 11. So, and B is actually equal to 6. So, this is 6 and A is 11. So, that's what I'm doing. 6 right is what I'm putting, 11. That is done. And what is the other thing that you're doing? B is left. That is B's, okay, I'll just write this property. A left. A left. A is left, that you're putting it as C. What is A? A is actually this, right? A is 11 and 6 is B. And 9 is C. So A is left. So 11 is left. 11. This is 11. Okay. And that you are putting it as C. That is 9. I hope you people understood. That is what we are doing. That is the modification that we are doing when we are rotating towards right. When we are actually rotating 6 towards here. When we are rotating 6 to 11. When we are rotating 6 to 11. Whatever that we have here, that will come as the right child of 6. Right child of 6. And whatever the right child that we have will be the left child of the original thing. Original node that we are doing. That is actually following the rules of the BSD, right? All the node values to the left will be less than the root value, and that would be less than the right side values. That's what we are doing. So I'll just erase this arrow mark so that will be much more clear. So when you're actually rotating this, when you're actually rotating towards right, your whole this particular thing will be coming to your right side of 6, right side of the 6, and all this right side of 6 will be the left side of your 11, because indeed all these things are less than 11. So I'll just try to put these things to the left of 11. That's it. Your tree would be much more balanced. I hope you people are understanding this point. So that's what we have done. So what is the thing that we have written here? I'll just erase these things. So what is the modification that we are writing? So I'll even erase this part. So first we are considering B, which is actually A is left, and we are considering C, that is B is right. And now to the B is right, we are putting A, and to the A is left, that we are putting C. If you just carefully observe, that is what we are doing. And this comes under right rotation. Oh, right rotation. Okay, right rotation. Right rotation. Great. This comes under right rotation. And when is this happening? This is also important. When are we going to do this particular right rotation? I'll even erase these points. Okay. So when are we going to do this right rotation? If your balanced factor comes out to be greater than 1. If you carefully see, here it is 2. Your balance factor is greater than 1, isn't it? Balance factor is greater than 1 in this case. And also your left, that data that you have entered right now, 4 is what you have entered, right? 4 is what you have entered. So if that particular data comes out to be less than like 4, like, or if I just mention this to be data, if I write this to be data. So if your data is less than node left data. Okay, so these are the two conditions. Great, these are the two conditions. Your node is this. Okay, this is your node, or A, anything that you would like to mention. So your balance factor comes out to be 1, greater than 1. Yes, here the balance factor is 2, which is greater than 1, and the data that you have entered right now, that is 4 that you have entered, right? 4 is the data that you have entered, and that came to be on your left side. That is your node left data, that is 6. Okay, the data that you have entered 4, that is less than 6, right? That is the reason it has went to your left, and that is the reason your balance factor came out to be greater than 1, because balance factor greater than 1 in the sense what? Height of the left tree, height of the left is much more greater than height of the right. That is the reason you are ending up with positive values, isn't it? So your data that you have entered, that is less than node left data, that is the reason it have entered into your left side of your node, and that is the reason your total balance factor got to be more than 1. Great. So I hope you people understood this particular things. Very evident, very easy to identify as well. So I erase these points. So what are the things that we have mentioned? So these are the following things that we are going to do, modifications. Like these are the following modifications, and the conditions are: first one, your balance factor is greater than 1. Second one, your data, okay, data is less than node. That's what we need to write, node left data. Okay, so in these two conditions, if these are the two conditions, then we need to do the right rotation. Great. I hope you people understood. This is the first case. So I'll just even erase this point. Great. Okay, this is 6. Fine. So I hope everything is clear for you people. So this is the case of first rotation. So before we proceed, we'll just do the basic coding first. Okay, we'll do the basic coding and we'll go through the next steps. So first thing is, let us assume the very first thing that has been given. Okay, very first insertion. When there is no insertion, like no tree that's already been formed, that's the first time that you're actually trying to form a tree. That means you will be having nothing. You'll be having, you will not be having anything to your that's already been constructed. It's the first time that you're going to construct something, right? It's the first time that you're going to construct something. So here, if you carefully observe, the values are just given. Okay, the values are just given. So you need to insert something. Initially your node is null. Because there is nothing that already been formed. It is completely null. So in that case, if not node, okay, if not node, return new node of data. Okay, so this is the first case where initially there is no tree that has been actually formed. That's completely null. Okay, to that case you're adding some particular new node, and that would be like this, new node of data. And second one, if if let us assume there's some tree that's already been found. Okay, let's assume that there's already some tree that's already been found, and your data that you're adding, trying to add, is less than the roots data. Okay, less than the roots like the thing that you have, like the node. That node data is less than like the data that you're going to add now is less than node data. Okay, let us assume this is one of the case. Great, your node data that you have so far, the node that you have, the recently added node, if your present data is less than the node data, you can just insert to the node left, isn't it? This is the rule of binary search tree, the very first rule. So do the same function, insert to AVL. Okay, insert to AVL of its left. Okay, nodes left and data. Okay, nodes left and data. And else, okay, else if your data that you're going to add, that is greater than nodes data. Okay, nodes data, then add it to your right side. Okay, add it to your right side. So insert to AVL, node right and data. Great, node right to your data. So initially we have the node already, we have the head of the head node, and now you're trying to add some data, and if that data comes out to be less than that head node, add to its left. Okay, add to its left, somewhere in its left. And if that data comes out to be greater than the node, the original, the head node, then add somewhere to its right. That's the reason we are putting node left and node right. Node left in the sense, after the insertion you'll be getting your left child, after the insertion you'll be getting your right child. I hope you understood. Else what are the other case? Other cases, like you are trying to insert some node that is also already equal to the node nodes data. All right, in that case you cannot insert it, because we want our tree to be duplicate free. Our tree will only be constructed if it is only having the distinct value. So in that case, just return the node. Okay, just return the node. So I hope it's done. So the initial point, construction, where are we putting all those things, is this. Now you need to find the balance factor. Okay, now you need to find the balance factor. So how are we going to find the balance factor? So we'll just name it as balance. So int balance is equal to get balance of node. Okay, get balance of node. We'll write that code also, balance of node. So how do we get the balance of node? I'll just go here. Okay, how do we get the balance? So int get balance of node. So how are we going to get the particular balance of the particular node? So that is basically return height of node left minus height of node right, isn't it? So this is what the thing is. This is the balance factor. I hope you people understood. So if in case the node is not defined, like if it's null, so in that case, like if it's null, return 0. That's it. So return 0. So like it's better if I just mention this to be some n. Okay, so just to avoid any sort of confusion. Great. So and this is n, and this is also n. Great. So we have got this. So if that particular node is not defined or it is null, return 0. If else, return the difference of height of left subtree and right subtree. And what is the height? We also need to write the height function, right? So int height of node, again n. Okay, so for this, okay, let me write this properly. So what is the height? How are we going to write the height? Return n height. Okay, if you see the struct of this, structure that has been defined, so you have the variable height already, structure of the node, so you can just return it. And if in case the node is not defined, if not n, then return 0. Okay, return 0. So I hope you people understood. So this is how we'll be getting the balance of the particular node. All right, if the balance of the particular node, this is how we'll be getting it. And what is the other thing that we have just configured, like the thing that we have configured? If your balance, okay, if your balance comes out to be greater than 1, and also your data that you have added, that is less than nodes left data. Okay, nodes left data. Okay, nodes left data. Fine. This is the recent conclusion that we have got. So in that case, you return the do the right rotation of your present node, okay, of the node that you're dealing. So here in this case, so we are doing the right rotation, isn't it? We are doing the right rotation. So left is being rotated like this, and 6 is coming to this point, this place. So you're doing the right rotation on 11, because in this case you are getting 2. In this case you are getting the disturbance. So this is where you'll be doing the right rotation. I hope you people understood. We'll be writing that right rotation also now. So what is our right rotation? So what is how are we going to write that particular right rotation function? So node right rotation. Okay, right rotation. So we'll be having the node now. Nodes star n is what, let us assume that is the value. So what are the things that we are doing? If we carefully see, we'll be first storing the nodes left. Okay, so initially we are provided with this, right? Initially we are provided with particular thing. Now we'll be storing its left in particular b. Okay, now let us write that. So let us write this as a itself for better understanding. So node star b. Okay, node star b is equal to a's left. Okay, a's left. Okay, that's the first thing. And what is the second thing that we are doing? C equal to b's right. C equal to b's right. So node star c equal to b's right. Okay, b's right. that is also done. And what's the third thing that we are doing? B's right is equal to A. Okay, B's right, I'll just write this here. B's right is equal to A. And what's the other thing that we are doing? A's left is equal to C. A's left equal to C. Great. Now we have completed the modification that we need to do. I hope you people understood the same thing that we have written. That's what we are doing in the code as well. Now after doing this, we also need to update the height of this, isn't it? Because now we have changed the things, we need to update the height as well. So how are we going to update the height? So the same simple thing. Once you have done the required stuff, just write this updated values. A's height is equal to max of A's height of A's left, okay, and comma height of A's right, and plus 1, isn't it? And also similar thing with B. So B's height is equal to max of height of B's left and height of B's right and plus 1. Okay, so we have updated the A's right and B's right, and you did not need to do the same thing for C because C's height is not being changed. If you carefully observe, the C's height remain the same. You are just inserting this particular C to the left of that we have to the left of 11, right? And all these are balanced in the sense it will be having -1 or 0 or 1. In this case it is 0, so you need not do it. Even it's -1 or 1, we are doing from the grassroots levels, we are doing from the start point, so you need not do any more changes to C. That's not actually required. Everything is being handled. Okay, so these are the things that we have updated, and finally we will be returning what? B. Why are we returning B? Carefully observe. So right now you're doing this particular thing, right? You're doing this particular thing, and once after it's done, once the rotation is done, what is your present left side of 14? That is 6. It's no more 11. Okay, it's no more 11. It's 6. So that's the reason we'll be returning B. Okay, returning B. What is B? B is A's left. That is originally 6. That is what we are returning. All right. That is pretty much clear. Pretty much evident. That's you must actually see this point. All right. Do not confuse. It's the 6 that we need to return as the left child of 14. It's not 11. 11 is no more the left child of 14. It is 6 now. So return 6. So that's what we have done. Return B. Great. Right rotation is done. So this is the first thing. All right, this is the first thing. If balance comes out to be 1 greater than 1 and data is less than node left less than data. So that is the first conclusion that we have got. And now frame the second conclusion. Okay, now what are the other cases left? Come to this particular case. There are 2 more cases, right? Excluding this case. Now we are trying to insert 45. When you do the insertion of 45, so I'll just copy this and paste this here. So once I do this addition of 45, where will it be inserted? Here it will be inserted, right? 45 is greater than 31, so come to your right. 45 is greater than 36, come to the right. 46 is greater than 41, come to the right. So here it will be inserted. Now you find the balance factor of each and everything. Okay, find the balance factor of each and everything. So here the balance factor of 45 is 0. What's the balance factor of 1? 41 minus 1. What's the balance factor of 33? 0. What's the balance factor of 36? Minus 1. What's the balance factor of 6? 0. What's the balance factor of 31? To the right we have 3, to the left we have 1, so it is minus 2. So here we have a problem. Now we need to do the rotation here. So how are we going to do the rotation? That is the question here. How are we going to do the rotation? So the thing is, here this particular 31, if I clearly observe, okay, I'll just erase these particular things. Now we clearly observe. So 31 is what having the problem because of the insertion of 45. Because of the insertion of 45, we are having the problem with 31. Now if I just put this to the left side, okay, if I just rotate this in the left, okay, if I do the left rotation, this is the left rotation. If I do the left rotation, 36 would be coming here, and your left rotation, that is 31, would be coming to this particular thing. So 31 would be your particular left child of 36, and indeed 6 is less than 31, isn't it? 6 is less than 31. So this whole part can be the left child of 36, isn't it? This whole part can be a left child of 36, and the left child of 33, can be a right child of 31, isn't it? So if I just erase this particular things, so what am I doing is because we have the problem with 31, we'll just exchange it with 36. When we do that with 36, this whole thing can be a left child of 36, and this particular 33 can be a right child of 33, because 33 is indeed greater than 31. That is the reason it is in the right region of 31. So we'll be adding this 33 to the right child of 31, and this 41, 45 will be same like that. We'll not be doing any changes. We'll only be doing changes with these things. So what are the things that I'm trying to tell us? So I'll just erase these points. The rotation technique modification that I'm trying to do is when I'm doing a left rotation. Okay, when I'm doing a left rotation, the following modification that I'll do. So let us assume I'm on this point. Okay, this is A, and this is B, and or I'll put this as B, and this is C. Okay, A, B, C. So what is the modification that I'm doing? So B's, okay, A's left is, A's right is, okay, A's right is B, and B's left is C. Okay, now we have got the values. We have represented some values. Now what am I doing is B's left, I'm putting it as A. So B's left, I'm putting this whole thing, like A is what the head of this, right? So I'll be putting that to the left of B. And A's right, I'll be putting C. A's right to the right of A, I'll be putting C. What is C? This 33. Okay. So when I'm doing this, I'm doing the necessary modification. So now let us write that. So I'll just cut it off first. Okay, I'll be putting it here. And now if I do the modification that I'm telling till now, so if I do that modification, so what I'll be resulting in, I'll be getting like this, 36, okay, and to the left we have 31, to the left we have 6, to this right we have 33, and to the right of 36 we have 41, and to the right side of 41 we have 45. Great. So this is what I'm telling. So now after the right rotation, left rotation, okay, after this being rotated towards the left, your 36 is a new head, and 36 left we have this whole part 31 6, okay, 31 6 have come here, and 36 original left is the right side of 31, okay, right of 31, and these things 36 and like 41 and 45 will originally be here, because the problem is with 36, which is having a more balance factor, that's -2, we are putting that to the left side of 36. Okay, so in that case, in that ways we are reducing the balance factor, for 31, and we are making sure that for 36 everything is balanced, because we have two things over to the right side of 36. So if it's better if we push these two to here, so the balance factor would be 2 minus 2, which is equal to 0. So for 36 it would be completely fine, no problem would be for 36, and 31 will also be satisfied. I hope you people are understanding these things. So this is the fundamentals of I'll just erase these arrows as well, like a lot of confusing arrows. Okay, so yeah, fine, I've erased these points. Okay, fine. So I've erased these things. So I hope you people understood what are we doing to do. This is a left rotation. This is a case of left rotation. What are the things that we are doing in the left rotation? These are the particular things that we are doing. And what are the condition for the left rotation? What are the conditions for the left rotation? If your balance factor, if your first thing is your balance factor turns out to be less than -1, okay, this is one of the thing. And second, what is the second thing? Your data that you have added just now, that is greater than nodes right data. Okay, nodes right data, isn't it? So whatever the data that you have added 45, that is greater than the nodes right data, isn't it? So it's greater than 36. That is the reason it have gone to 45, and that is the reason the balance factor came up to be less than -1. When your height is more on the right side, your balance factor will be reduced than -1, more like it will be going to the negative side. So that is the reason, because your data has been added to the right side, your balance factor turned out to be less than -1. I hope you people understand. So these are the conditions when we are going to do the modification, and what are the modifications that we are going to do? These are the modifications. So now let us list out that as well. So if my balance factor, okay, if my balance factor turned out to be less than -1 and data that I've added is greater than nodes right data, okay, so if these two conditions are met, I'll be doing return left notation of node. Okay, this is what I'm going to do. And if I just write that here, so node right rotation I've written, and this is now for left rotation. Okay, node left rotation node star A, we'll just use A itself. So what is the thing that we are writing? So first we'll be having A's right equal to B, so node star B equal to A's right. Okay, A's right, A's right. And what's the second thing that we are going to do? B is equal C is equal to B's left. Okay, node star B equal to C is equal to B's left. Okay, and what is the third thing that we are going to do? B's left equal to A, so B's left equal to A. Okay, and what's the fourth thing that we are going to do? And A's right equal to C, A's right equal to C, A's right equal to C. So these are the modifications that we are going to do, and we'll also need to make sure we are updating the height. That is very, very important. If you miss it, everything will be going wrong. Okay, so that's very, very important that you need to do. So A's height, okay, A's height is max of, I'll just write it properly. So max of height of A's left, comma, height of A's right plus 1, isn't it? And what is B's height? B's height is equal to max of height of B's left and height of B's right. Okay, and plus 1. That's it. So and then return, what are you going to return? The same thing, the similar fashion, return B. Okay, it's very, very important. Why are we returning B? Once you do the left rotation, your like the particular thing is being changed. Now initially that you have considered, which is actually equal to B, right? This is the B that we have done. Now this is what you're going to return. This is the new head or new something, like the new particular node that you are actually assuming. Your A is no more at the position, it's B in the position of A, so you need to return B. Great. So that's what we have done. Very, very important thing to be noted. I hope you people do not confuse with these particular things, right? So right rotation is done, left rotation is done. So we have got this. And what are the two more things that I'm actually trying to tell? So this comes to the third case. Now in this case, we are trying to add 8 to this particular BST that has been given. Okay, this is the original BST. Now we are trying to add 8. Now let us try to add 8 at the correct position. Okay, so I'll just copy paste this. So I'll just add to the 8 to this particular point. Okay, so where can we add 8? If we carefully observe, 8 is less than 14, so go to the left. 8 is less than 11, go to the left. 8 is greater than 6, go to the right. 7 is less than 8, so go to the right. So you can insert 8 here, right? You can insert 8 here. So I'll just erase these particular things first. Now do the BST. Now check the balance. Okay, so balance here is 0, here it is 0, here is 0. What's the balance factor for 7? It is -1. For 5 it is 0. For 6 it's -1 again. For 16 it's -1. For 11 it is what is the balance factor here? So the maximum that we have to the left is 3, and to the right side it's 1, so it's -2. Okay, so here to the left it is going up to 3 levels, and to the right it's going only up to 1 level. So 1 minus 3, that is equal to -2. And coming to 14, 14 the maximum it's going up to is actually 4 levels. So to the right side it's going to only 2 levels. So again it's -2. So the problem is being created here, right? The problem is here. There is disturbance here. So now how are you going to do? Now according to the previous convention, okay, now according to the previous convention, if you feel like, because now we have got the problem here, and now if you try to modify it, if we try to modify it by the right rotation, if we try to do the right rotation, will it work? Now let us see that. If we do the right rotation, will it work or not? So I'll just erase this point. Okay, I'll just erase this point. I'll write here. So 14, and this is 16, and this is 17. Let us assume I'm doing the right rotation now. So if I do the right rotation, I'll be having 6 here, and I'll be having 11 here, and I'll be having 12 here, and to this particular 6 left we can have 5. Okay, and to this 11th left we can have 7, and to the 7th right we have 8. Okay, now if we carefully observe, is that being solved? Like, is it being solved? Do we have this particular solution now? Check for 6. 6 left is actually having a height of 1. 6 right is actually having a height of 3. 1 minus 3, that's equal to 2 minus 2. Is it solved? Is it fine now? No, it's still not fine. It's still not a BST. This left rotation did not work. Left rotation alone did not work. That is what I would like to mention. Left rotation alone did not work. So there must be something that we need to do. All right, there must be something that we need to do before we are doing this particular rotation, or proceed with some other rotation. So what is that? We'll observe that right now. So I'll just erase these points. I'll erase this particular thing. So first of all, let us observe where this problem is being framed. This problem is being framed after we added 8, isn't it? After we added 8. Now let us cut the unnecessary heights. Let us cut that unnecessary heights. We see that 7 is basically greater than 6, isn't it? 7 is basically greater than 6, and this whole 6 is less than 7. So we can happily insert this particular thing to the 7, isn't it? And we can have like this 7, 6, 5 and 8, isn't it? So in this fashion we have reduced this height from 7, isn't it? From 7. So from originally it was like this. So like now we have replaced this 7 with 6 and this 6 with 7, and now we have got this particular thing. And now if we do this right rotation with particular this 11 after getting this 7, so if we have 11 here, so if we do this rotation here, we can have like this 7, 11, and to the left of 7 we can have 8, to the right side of 11 we can have 12. So 12 is basically nothing but the thing that we have here. To the right side of 11 that was originally there, that will be there itself, and to the left side of 6 we can have 7, we can have 6, and to the left side of 6 we can have 5. Great. So this is how we can do, getting my point. So basically what we are doing is, initially we have done the left rotation, we have done this particular left rotation here, we have done this left rotation, and after this left rotation we are doing this particular right rotation. Okay, we are doing this right rotation and minimizing our heights. We are not using unnecessary heights. We are making sure we are only using the height so that the tree would be balanced. Okay, our main intention and goal is to make sure the tree is balanced, right? So because the problem started from here, if I just need to tell that once again, so here it is 6, here it is 7, here the balance factor is -1. Great. So because here we have this particular 7 which is actually greater than 6, we can happily insert this whole part to the left of 7, isn't it? So that turns out to be 7, 6, 5. So we have, into the right side we have 8. Now we can put this 7 to the left, to the left of, or we can just interchange with 11. Once we do it with 11, we can have the 12 to be in the right side of 12 itself. But because this whole part is greater than 7, we can put it as the right side of 7. Okay, because we have this balance factor to be -2, we need to reduce it. We need to reduce in some or the other way. We need to we need to reduce the height that is there bottom of the 11. That is what we are trying to do. So we have exchanged that with the 7. So initially we tried doing it with 6, but that did not work, isn't it? It's still giving a failure. So but right now if we do it with 7, after doing the left rotation we are doing a right rotation, it works out. So if I just need to write the conditions of it, I'll just write the conditions so that you'll be getting a better clarity for sure. That will give you a better clarity. So I'll just write it here, and I'll just take it off. Okay, I'll just take it off. So after doing a single chain, after doing a single modification, what I'll be getting is 14, 11, 16 and then 17, and after doing the right rotation, okay, after doing the right rotation I'll be having 7 here, and I'll be having 6 here, I'll be having 5 here, and I'll be having 8 here. Okay, this is what I'll be having. I'll be writing properly. So I'll be having 8 here. Great. And after another iteration, okay, after another thing, so what I'll be having here is I'll be having 14. So now I'll be doing, now what I've done initially at this particular point, 7 I've actually rotated with 6 left rotation 7. Okay, now I'm doing the right rotation with 11. So once I do it, what I'll be getting 14, this will be 7, and to the right side of 7 I can have 11, and to the 11 we also have 12. I missed it out. So we can have 12 here, and to the left side of 7 we can have 6 as usual and 5 as usual. Okay, and did we miss anything? Yes, 11's okay, 7's right, that can be 11's left. Okay, 11's 8, and this is 16 and this is 17. Now if you carefully observe, everything is balanced, isn't everything is balanced? The balance factor here, so if you just write, this is 0 0 0 and this is 0, and for 11 it is 0 again, for 6 it is 6 it is 1, and for 7 it is 0, for 16 it is -1, and 14 it goes up to 3 in the left and 2 in the right, so it's 1. So everything is balanced now, everything is balanced. What is the thing that we have done? We have done left rotation here, and we have done the right rotation here, So left rotation is once we are doing, and then right rotation. But what's the condition? What are the conditions? First condition again, your balance factor turned out to be greater than 1, isn't it? Your balance factor here, if you carefully observe, where is the balance factor? So in this case your balance factor is particularly okay, so in this case 3, okay, it's not -2, I've done mentioned it wrong, it's to the left that you have greater, right? So it is 2 and 2, great. Your balance factor is greater than 1 in this case. And second one, what is the second one? Your data that you have added just now, okay, the data that you have added, 8 is what you have added, and the data is actually greater than nodes left data, isn't it? So 11 is where you have got the disturbance, and what is the data of that particular node that to the left of it? That is 6, and for 6 you're adding to the right side. Before, if it is left, then we would have done the left rotation only, but now you have done to its right, now you have added to its right. Because of that case, we need to do the left rotation first, and then we need to do the right rotation. Great, getting my point? So we have added this particular node, that new node, to the right side. So node left, the data that you have added, that's 8, that's practically that your that is greater than your nodes left data. Nodes left data in the sense that is 6 is less than 8, so 8 is being added to the right side of 6. That is the reason we are doing first a left rotation, just to understand these things. Okay, just to understand these things, so that these will be sorted first. Okay, whenever we have this particular thing, we need to sort this. So once it is sorted, now we are doing a right rotation. I hope you people are getting it. So once we do, first we do the left rotation, and then we do the right rotation. So, and we'll write the same. So before that, it's important that we update the height here. Once we inserted, we need to update the height. That's what I've said at the beginning. So height of nodes left and height of nodes right. Okay, and +1. So +1. And now what is the thing that we have just concluded? If balance turned out to be greater than 1, and your data that you have added is greater than nodes left data. Okay, nodes left data. In that case, do the left rotation first. Okay, on what are you doing the left rotation? You're doing on your left side. Okay, you're doing on the left side of 11, isn't it? That's where you're doing the left rotation. That's very, very important. You're not doing on this particular node. You're first doing the left rotation here, and then you're doing the right rotation. So node. So if I just represent your node left would be the left rotation of nodes left. Okay, nodes left. And now after doing this, do the right rotation onto your particular node that you're standing. Okay, right rotation, and return it. Okay, return is very important. Return it. So this is the third conclusion. If your balance turned out to be greater than 1, and your data that you're adding, it's greater than the nodes left data, then you need to do the left rotation first. This is the left rotation, and then do the right rotation. I hope you people understood. This is the fourth case. Okay, now where can we insert 16 here? So 16 is greater than 6, come here, come to the right. 16 is greater than 8, come to the right. 16 is greater than 10, come to the right. 16 is less than 17. So add it here, add to the left of 17. Okay, so once we have added this particular things according to the first rule, calculate the balance factors. What's the balance factor? This is 0 here, 0 here, 0 here, and this is it's +1 only, and it is +1 here, and it is -2 here, it is +1 here, and sorry, it's 0, okay, it's 0, and here it is -1. -2, and here we have -1, and here we have -2 again. All right, so these are the balance factors of each and everything. Don't mind if I've calculated anything as wrong. You can do it later, it's not really important. So now we see that the problem is being raised here itself. Okay, the problem is being raised here itself. So try to do some modification to the right side of 2. Okay, to the right side of 2. What am I going to do is, so this particular 17, okay, this particular 17, I'm going to do a right rotation. What happens if I do a right rotation? So that becomes like this. This becomes like this: 10, 16, and then 17, isn't it? 10, 16, 17. This comes in this particular lane, and we have 8 to the above of 10, and we have 7 here. And if we do this particular left rotation, now we have done the right rotation. Now if we do the left rotation, okay, now if we do this particular left rotation at this particular point, what happens is we can get 8 here, we can have 7 here, we can have 16 here, all right, we can have 16 here, and to the left we can have 10, and to the right we have 17. So everything is balanced now. Everything is balanced. Because this is balanced, this is also balanced. Initially we were having like 3 to the right side of 8, right? This is 3. Now after doing this, we have only 2 to the right side of 8, right? This is only 2 to the right. So once we have 2 to the right and we have 2 to the left of 6, this would be 3 total. So 2 minus 3, that's equal to -1. It's sorted. Great. So that is what we can check. Everything is balanced after doing this particular thing. What did we do? We are actually actually done the right rotation first. We have done this particular right rotation. This node is what we are doing. On this node, we are doing the right rotation. First, we have identified the disturbance here. At 10, we are facing the disturbance. So what you are going to do is do the right rotation onto your right child of 10. Onto your right child of 10. Do the right rotation on right child. Node right. Okay, node right. Do the right rotation on it. Once you did the right rotation, now you do the left rotation. Now you do the left rotation of 10 with 16. Once you do it, everything is sorted, right? Once you do it, this particular 10 can come here. The height is now minimized under the 8. Under the 8, the height is minimized. That is the reason we are doing a left rotation. We are not doing it for a fun sake. Once we do the left rotation, this whole thing can come up to your left of 16, and this will reduce the height under 8. If it's reduced the height under 8, overall under 16 also it will be reduced. That is the main intention. And for this to happen, you need to make sure 16 is having here. If in case 17 was there here, okay, if in case 17 was there, and if you are trying to do the same thing with 17, it would be like this: 8, 7, 17, and to the left of 17 we would have been having 10, and to the right side of it will having 16. Is that giving any optimal solution? No, it's not giving you any optimal solution. It's still having we are having a height of 3 under it. This is not the thing that you are supposed to do. You are not getting anything out of it. So that is the reason you're doing a right rotation first, and then you're doing a left rotation. So but what are the conditions in which you're doing? So first one, your balance factor comes out to be less than -1. Okay, that is the case when you're doing. And second case, when are you going to do like what is the second condition? Your your data that you have added. Okay, the data that you have added, that is less than node right data. Okay, the data that you have added, that's what 16 is what I have added. That is less than, that is actually less than nodes right data. So here is what you are facing disturbance 10. What is nodes? That is right side of 10. We have 17, and to its left, that's what we are adding, right? To the left of 17, we are adding 16. That is where the disturbance have come, because we have added 16. The disturbance has started and resulted at 10, and we are doing the right rotation to the right side of 10, and then we are doing the left rotation on 10, so that everything under 8 gets dissolved. From 3 it has become to 2. Everything has been solved for 8, and then indeed it's satisfied with 6 as well. So your balance factor comes up to be -1, and your data that you have added, that is less than node right data. Then this problem comes up. If it would have been something like added to the right only, then right rotation will absolutely work, nothing else to be done. But because your data that you have added, that is actually less than nodes right data, so we are getting this particular problem. So if I just write this particular thing, so after the final modification will look like this. Okay, final modification will look like this: 6, 3, and we have 8 here, and we have 7 here, and we have 16 here, and we have 10 here, we have 17 here, and we have 2 here, and we have 5 here, we have 4 here, right? So if you can carefully observe, everything is sorted. This is 0, 0, 0, and this is 0, this is 0, this is 1, this is 0, and for 8 we have -1, for 3 we have -1, for 6 it is 2 and 3, that's again -1. So everything is fine now. Everything is fine. Everything is satisfying the property of BST. All right. So this is the thing. So we'll just write that condition as well. If your balance, okay, if the balance turns out to be less than -1, and your data that you have added is less than node right data. Okay, node right data. So in that case, you do the right rotation. Nodes right is equal to right rotation onto your nodes right. Okay, nodes right, and return left rotation. Do the left rotation now. Do the left rotation on your particular node. All right. So after doing this whole things, return the final node. That's it. So you have completely understood like what are you doing at particular conditions, if your balance is greater than 1, and where is the node being added. Only on those two factors we are doing different sort of modifications. Great. So it turns out to be left, right, left, right, and right, left. Only 4 conditions. And at every point you are trying to make sure you're updating the you're doing the rotation successfully, and then also updating the heights. Okay, updating height is also very important. If it's not done, everything will be collapsed. All right, that's very important. And return the correct things. Okay, once you have done the rotation, your roots have been changed, like your nodes have been changed. That's not the node that you're working upon. Your new node has come. So return that particular things. All right. So these are the some of the things, and height and balance. Now let us try to run this. So this is practically a long video because it's a tough question, and we have to do a lot of things, and I'll even submit for your reference. It should be submitted successfully. Let me see that. Okay. Yeah, fine, it worked. And yeah, items number 1. Yeah, fine. I hope you people understood. So if there are any doubts, feel free to comment in the comment section. And for your reference, codes in Java, Python are given in the description. Please go through them. So yes, it is a long video. Try to do the dry run. You people will understand. The main objective here is to reduce the unnecessary length, unnecessary height that is there in why is it being like this? Okay, so unnecessary height that is there under each and every node, and for that reason we are doing the left rotation and right rotation. And for that space complexity and time complexity stuff, TC is actually equal to O of logN. The reason being, so the height is what the maximum thing that we are doing is like it's the height of the binary necessity that is actually equal to logN. Okay, number of nodes that are there. So we are only working on those like till that height only, right? We are trying to do the rotation or anything. Rotation, if you see the code for rotation, we are not doing something like something that actually costs anything, like it's just a constant part. That's it, right? We are just trying to change the addresses, and that's it. We are not doing anything. And even height you are getting in a single code. You're just getting that in a single code. You're not trying to do the traversal and all, because in your struct itself it's being stored the height. So you're not doing anything. It's just that you're doing your work onto the maximum height. That's it. And your space complexity is also the same, O of logN. So or the height of the height of the tree. That's a recursive stack space that you're using. And time complexity is O of logN, because that logn number of nodes is what you're actually visiting and trying to do the the thing that is required, the modification, the change, or the putting of the values at the right place, everything. I hope you people understood this. So thank you for watching, guys. Stay tuned.